All right, good morning, everybody. Good morning. All right, so a couple quick things. First, I hope everybody enjoyed their Friday off. And this Friday's mental health thing, there is going to be a guest professor. So those of you who have electrical engineering friends who are taking that intro to computing course, you know what that's going to be, but you might have a furry friend show up on Friday. So those of you who are missing a little slice of pet from home, I am bringing in my dog, the pup professor, and she'll will go around and be nice to everybody. So that's something you can look forward to on Friday. So get everybody on the same page about what I'm expecting. I know I sent the email out, but I just want to make sure that everybody knows and you have an opportunity to hear it. Check your email if you don't know what I'm talking about. So you have to have your first meeting with your program manager done by today. If you haven't done that yet or that hasn't been arranged, get that done. They should have reached out to you. If that hasn't happened, let me know immediately. They've reviewed your project proposal, and the first meeting, what they're doing is going to give you constructive feedback. They're going to tell you about ways you can improve the proposal, and what I want you to do is to take their feedback and make an edit to that proposal and upload it to the Google Drive by tomorrow night. If you do that and you do what they ask you to do, that's going to be an automatic 200 out of 200. You might have lost some points on your project proposal, but getting an edit and addressing that is it's going to be another 200 out of 200. So that's the way to bring the grade up. From there, you're going to schedule weekly meetings, and they're going to perform code reviews. So my recommendation is make sure that you have that scheduled at a time that all of you can consistently attend. Right? So I'm going to be teaching them how to be a program manager and how to give you guidance on that front. And what you're going to do is you're going to continue to work on your assignment. They are going to look at your deliverables based on what you have on your project proposal. And each week you're going to evaluate, are you actually meeting those? What are some of the challenges you're facing? How can we overcome those using our knowledge of data structures and computer science to be able to address those challenges? And so I will keep you up to date, and I'm going to tell you in the last week what you need to do in order to email your industry mentor in order to schedule a final presentation. All right, so now that I've got all that out of the way, in today's lecture, which I'm calling Casuals Everything Around Me, we are going to discuss some more advanced topics. So the data structures that we've covered up to this point, so we've learned about dynamic arrays, we've learned about hash tables, we've learned about different forms of hash tables, such as a double hash, we've learned about linear probing, open addressing, we've learned about binary search trees, we've learned about AVL trees, we've learned about B trees, we've learned about red-black trees, we've learned a bunch of stuff about graphs, about adjacency matrices and adjacency lists, and how to perform depth-first search, breadth-first search, topological sort, minimum spanning trees. Everything we've done up to this point has basically assumed that what we want the person to do is what they're going to do. Right? So I have an example, I have a red-black tree here. And this red-black tree is really good for an average search time. Big O of 2 times log n minus 1. That's pretty good. We have relaxed balancing mechanism, so we have an advantage over the AVL tree in that respect. However, let's just say we have a weird customer, a zany customer, that says, all right, is 2 in the tree? Yeah, it's there. Cool. I can just go 10, 4, 3, and 2. Okay, is 2 in the tree? Yes, 10, 4, 3, and 2. Is 2 in the tree? Why do you keep asking me for 2? I set up this whole thing with all this balance, and you just keep asking for this really, the same thing over and over again. It doesn't make any sense. So you kind of lose some of the benefit of the whole point of setting up the data structure in the first place. So the same thing with sorted doubly linked lists. We get a disadvantage, so you learned about this and you applied them to do priority queues, right? But if I just put them in order, there's no benefit. I lose the whole point. Like, why'd you give that to me in that order when you already had them sorted? There could have been a different data structure you could have used. So in short, and there are times when the user acts zany, like the Animaniacs, those throws a wrench in our well-laid plans. So the kind of meant computational thinking that you want to start applying moving forward, and this will really benefit you when you hit programming paradigms and then algorithms especially, is this idea when there's not an exact answer. And we touched a little bit on how it is that we might want to account for an exact answer when we talked about this idea of amoritized analysis. Does everybody remember what amoritized analysis is? Let me put a skip here so everybody on the chat wants to answer as well. Remember what this is? Yes. Yeah, we have this average case where we think about all the possible cases and we come up with the average case over time. Now, the reason why this is good, so first of all, absolutely right. And now the reason why this becomes beneficial is we want to build up credit. If we have a lot of operations that are very short, but in order to gain those short operations, we have an occasional worst case operation. This is when data structures and algorithms that apply this kind of amoritized analysis become beneficial. So designing data structures that trade off per operation efficiency for overall efficiency. So it's not quite as efficient if we have this ideal base, but it's really good for what it is that we're trying to do. So I showed you in lecture this equation where we had to get for every possible operation, the amoritized cost will be greater than the cost of all, greater than or equal to all the cost of all the possible operations. We account for this occasional worst case scenario. And so on exam 1, you had to calculate the amoritized analysis. And we're trying to figure out this really good scenario that we want to use. And so for inserting into the dynamic array, which I'll just skip over this slide because this is a review, but the whole idea is that we're putting things onto the end, and that doesn't really give us any information. So for a dynamic array, what we did is we have to recopy everything when we're inserting once we've exceeded the length of the internal static array. So we have to reallocate a new array, copy them all over. And that's why in this particular chart, you see that there's this occasional jump. Most of the time, we just have this continuous big O of n, but we have this occasional jump due to the copies. But the trade-off is we can abstract having to reallocate that memory from the user, which is why using a vector in many circumstances can be very easy for you. Using standard vector becomes easy to implement because of the occasional trade-off there. And then we compared it to big O n log n. We saw that actually this is better than having to worry about other things. And especially if we go to big N squared, which would be a worst case scenario, then it becomes significantly better. And so nothing in computing is perfectly simple. And what I want to do is I want to introduce you to a concept that some of you, I think you might have encountered this already in logic design if you've taken logic design. And you definitely will encounter it in computer architecture. And it's known as cache memory. Are you familiar with levels of cache? Okay, there's a lot of heads nodding, good. All right, so the whole idea behind cache hierarchy is that what we want to do is that we want to trade off between the speed of being able to access memory and its cost, right? So the very fast local registers, which we've learned about because they're the base addresses for pointers. Right? For these really fast local pointers, these last local registers, they're very expensive. They use SRAM memory. The memory will get slower, but it's cheap. It means we can store more information in there. So what we want to do is we want the memory that we can access the fastest to be in our architecture that we can access it quickly to perform those operations. And then once we use all this information, we want to swap it out in the slower memory to bring in new information to one fast, right? And we call this the principle of locality. So when we allocate memory, a program that tends to access data forms a physical cluster in memory. And we now understand this because of what we've learned in data structures. We allocate a dynamic array. It's all right next to each other. We have pointers in a linked list. They tend to move and they tend to be in the same kind of cluster. Programs on the stack are also very similar and close to each other in that location. And so as a result, there's two types of locality And we're going to use the data structure that we're going to learn about today called a Splay Tree to exploit locality for amoritized beneficial performance. Temporal locality and spatial locality. Temporal locality says if an element is referenced, it tends to be referenced again soon. And if we think about this, it makes sense. If I create a variable, I'm going to use it to perform a task. And odds are I'm going to use it multiple times to do that task. With spatial locality, since we're putting everything close to each other in memory, if a memory element is referenced, memory elements whose memory addresses are close by tend to be referenced again soon. So if I'm writing a program, I'm going to be certain locations in memory, and then we have while loops, right? We got recursion, but they all tend to be clustered in the same place. Likewise with the data structure, if we go through the this pointers and we analyze where all the memory locations are, if we do like a void pointer and find everything out, we're going to see that all those memory locations tend to be close. And if you remember, when you print out the registers, if we print out the memory addresses, the registers had these really long sizes, but then the things that were in data memory had shorter locations, values. They're about like 10, 0x, and then had 10 numbers. The reason why is because it still can be represented with that full memory, but we're just bringing a small portion of it into a smaller cache level. So that's why that address is shorter. And so what we're trying to do is we're trying to take advantage of performance in order to be able to run a program. And so here is a diagram of cache memory. So in the CPU, this is what we've learned about so far. In logic design, you're generally learning about, and I briefly touched on this at the beginning of the semester to help you understand what a pointer is. We have instruction memory, we have data memory, we have a arithmetic logic unit, you have a control unit, and you have a program counter, and that's all inside that box that says CPU. Then you have, but that data memory expands out into these different levels of cache. So level 1 cache, you have a really small amount of memory, but it runs faster. Level 2, there's more of it, but it runs a little slower. Level 3 runs even slower than that, but we can have more of it because it costs less. And then main memory is the non-volatile memory that we'd use to be able to save information after the program terminates. So the whole idea behind this different levels of cache is it's a design choice to figure out the best possible trade-off between program speed and cost. And so the way we exploit this, okay, I'll just run this here. So at the beginning of the semester, I ran this command lscpu, right? And I told you that towards the end of the semester, we have a much better understanding of what all this stuff meant. So we have an x86 64, so we have a 64-bit architecture. We have 32-bit mode and 64-bit mode. So if you remember that -M64, we're using 64-bit mode in our operation. In logic design, have you all learned about big endian and little endian yet? No. Okay, so TLDR version, big endian means I would start at the left and that would be my most significant bit and work right. And little endian, I start from the right and work left backwards. So we have 8 CPUs that are allocated to this particular thread. A lot of this is operating systems. When we get down here, we see megahertz, so it's running at 2.3 gigahertz. And then we have these levels of cache. It says L1D cache and L1I cache. So that's the instruction and data memory being split up into a fast instruction stack and a fast data heap. And so here we have 64 kilobytes of that. And then level 2 cache is 512 kilobytes, so we're able to store more information in there, but it's a little cheaper. And level 3 cache, now we're up to 2 megs. And then you get into gigabytes of main memory. And here, if you want to review it, I also have all the information that's available. Most significant bit here is on the right. Here, in this case, I used a different machine, so it's an Intel Xeon model. And we have the CPU speeds, level 1 data memory cache, level 1 instruction cache, level 2 cache, level 3 cache. And so this is a quick example of a problem that you will work on in computer architecture about cache memory trade-offs. And so I won't go into too much detail about something called average memory access time, but the general idea is that if I have a level 1 cache, right, and I have my regular memory, my regular memory takes 100 nanoseconds, so it's very slow, and my level 1 takes 5 nanoseconds, and I have a 95% hit rate. That means 95% of the time I will find what I need to find in level 1 cache. However, 5% of the time I need to use these 100 nanoseconds to bring in information to the level 1 cache and run it. So if I have 0.95 times 5 plus 0.05 times 100, this adds up to 10 nanoseconds. So on average, the operations take 10 nanoseconds. So if I add a level 2 between them, which is bigger, but it will have about 85% of the hit rate, and an access time of 7, so it's slower, this will bring the access time down to 6.1. And if I add a level 3 cache of access time 10 nanoseconds, it reduces the average memory access time down to 5.575. And after level 3, what you'll see is that the benefits really kind of start leveling off. So you're starting to add more cost to the computer without gaining much benefit. So the whole goal is I'm reducing it from 100 nanoseconds per operation down to 5.75. So the million-dollar question is, why does that matter? Well, we have to be able to use data structures to be able to access and keep track of what elements are part of our program. So in a spatially, if we use spatial locality, what this is going to mean is that our elements that we want to access tend to be closer to each other in the data structure as well. So let's say that the elements I wanted to use in my program are all down here in the red-black tree, 2, 3, 4, and 5. Ideally, what I would like is I'd like these up here and all these other ones to be far away, especially if we're dealing with kilobytes and megabytes of information. So is there a way in which we can develop an amoritized approach to getting the elements towards the top of the tree so that way we can access them to take advantage of this temporal and spatial locality? And our trade-off would be that occasionally we'd have to do a swap. So we'd have to go down to the bottom of the tree, bring some elements to the top of the tree, but then we would have 95% of the time where all the elements would be on the top. Does everybody see that? So how can we use a data structure to be able to do this? And so the data structure that we're going to use to do this is called a Splay Tree. And the process of bringing a node up to the top is called Splaying. And these are really good for cache memory. And the main idea is that the most recent accesses are closer to the top of the tree. We are also going to maintain the ordering of the tree, meaning that the same kind of binary search tree ordering that we've had in binary search trees and AVL trees and red-black trees and B trees is going to be maintained in a Splay tree. So our occasionally costly operation is going to be getting these elements from the bottom to the top. However, because we understand about temporal and spatial locality, most of these elements are going to be reaccessed, which means once we get them to the top, if we just keep accessing the few, like 8 or 9 that are close, we're going to be able to get significant performance benefit by using this kind of data structure. Hey, does anybody have any questions before I start digging into what these trees actually look like and do? Now, let me check the chat as well to see if we have any questions there. Okay, so this is where zig-zig and zigzag become really important. So what I want to do is I'm going to call this a zig. So we can either, if we do zigzag, that means it's going in opposite directions, but zig-zig goes in the same direction. With Splay trees, we're going to have 4 different rules. We're going to have zig, zag, zig-zig, and then zigzag. So this first one is called zig. And so what I'm trying to do is I'm trying to move 3. I'm accessing 3 and I'm trying to move it to the top of the tree. So what's going to happen is I'm going to move this up, and in order to maintain the ordering, what's going to happen is 4 is going to become 3's right child, and 2 is going to remain 4's left child, and the rest of the tree is going to remain the same. So we see that we're kind of splaying this up. And likewise, what's going to happen here is I have 5, and 5 is going to move up. 5 is right child will remain 6. 5's left child was null. And so what's going to happen is 4's left child is, and 4's right child is going to become 5's left child. So 5 and 4 with a null, and then we have 3 and then 2. So basically what we're doing is we're going to perform these splay operations where at each level we're going to see it move up to the top of the tree. In zig-zig, what we're doing is we are going in the same direction twice. We have left and left. So here we are moving 3 up to the top of the tree. Now what's going to happen is, at the first step, we're going to move 4 down to be 3's right child and move 3 up to be 10's left child. So that's going to look like this. So that's the first step. And the crucial thing to bear in mind is that we're moving 3 up, which means 4 is going to become the right child and 5 will remain here, which means we have 2 there. So we go back and do that step again. We see that it is moved up. And then what's going to happen is we now have to account for this part. So what's going to happen is now 3 is going to be at the top of the tree. 10 will become its right child. And then 10's left child will become 4. And then everything else down at the bottom remains the same. So that's what's going to happen here. And we're going to see that 3 is now at the top of the tree. We have maintained the ordering of the tree. And so let's say I wanted to move 5 up. What do you think I would want to do first? Let me press escape so that way those of you in the chat can do this as well. So if I want to move 5 up to the, if I want to splay 5 to the top of the tree, what do you think we should do? What's the first step? Okay, got 1 response in the chat. All right, so Fang Kong says, make 4 the left child of 5. So that's our good first step, right? So very good, that's absolutely right. So now we've moved 4 down. We're now going to make 5 the left child of 10. So now that we have this, what will be our next step? Yes. Very good. So now 6's left child is going to be pointing to, 10's left child is going to point to 6, and 5's right child is now going to be 10, and 3 is now going to be pointing at 5. So we have one last step here. What are we going to do? We want to get 5 to the top of the tree. We're almost there. Right now, 3 is at the top of the tree, so the tree looks like this. It looks 3, we have 5, 4, 10, all the way over here. So now we have 2 over there. So how would I get 5 to the top of the tree in this scenario? I give you a hint. You did the exact same thing with AVL trees. Okay, we have several responses in the chat. All right, move 3. Okay, so we want to move up 5. So Hector is correct. So what's going to happen is we are going to move 5 up, and then 3 is going to be here. And now we're going to replace this and make 4 the right child of 3, and 2 will be up there. So very good. That's absolutely right. So I have another scenario where I want to do zigzag. and now I want to move 5 up. In this case, I'm going to rotate and move 4 down. And then I'm going to make 10 the right child of 5, like so. And so the elements that are going to be at the closest of the element to the top of the tree are going to be the ones that we've accessed the most recently. Furthermore, and I've said this, but I just want to kind of hit on this again just to make sure that I'm driving this point home. The ordering of the tree is maintained throughout the entire process. So let's do an access, going through another example. Here we're going to make 4 the right child of 3. So it'll move over like so. And then we're going to make 10 the right child of 3, and then we're going to make 4 the left child of 10. Like so. So now what I want to do is I want to get 4 to the top of the tree. So I'm accessing 3 and 4. So now what I'm going to do is I'm going to move 10 up. I'm going to move 4 up. 4 is going to become the right child of 3. 10 will become the right child of 4, and then 10's left child is going to become 5. Like that. And then I'm going to do, so now I'm doing a zigzag, which means that 4 is going to become the top, 3 is going to become the left child of 4. And so we see here that the most recent elements are now the elements that are close to the top of the tree. And at the beginning of the example, 10 was the element that was at the top. So we see that all the elements that we've accessed are close to the top, while simultaneously we've maintained the ordering of the tree. So here's another important thing and a benefit of Splay Tree. So I talked briefly about this idea of 95% of the elements are in the cache, right? Which means that 5% of the time we might not find something. This is a bit outside the scope of the class, but that's known as a cache miss. The important thing in data structures with a Splay tree is that if the element is not in the Splay tree, we still perform splaying. The element that is, we find the element that is closest to the value that we wanted to insert, and we splay that element. So in this case, we want to find 6. So we would go through here, we'd say, well, 4, 10, 5, and we get to the end, right? Since 6 is not in the tree, what we're now going to do is we say, well, 5 is the closest element. We're going to splay that up. So what's going to happen is we're going to see that 10 is going to become the right child of 5, and then 4 is going to become the left child of 5. And we do that despite the fact that 6 is not in the Splay tree. But the reason why is because that is the closest element in memory to the one that we tried to access. So let's go through. We see that 5 is now at the top, just as we predicted. So and again, we're going to do 18. Now 18 is not in the tree. So we're going to splay. The way this will work is, well, 18's bigger, 18's bigger, and we get here, and now 25 is what is the closest value to 18. So what's going to happen is 15 is to become the left child of 25 in the first step. Okay, so that's the final step. So let me walk through step by step. So what's going to happen is 25 is going to have 15 as its left child, and eventually it's 12. And then I'm going to splay again. So we're going to see that 10 is going to become the left child of 25. And then 5 is going to be. So we actually see that we move these elements up like so. All right, so revisiting building credit. Now, the thing to bear in mind as we move forward in using Splay trees is that there is a worst case scenario for using them. So what I want to show you is I want to put in a Splay tree in order. So let's say I do 1, and I'll put in 2, and what we're going to see is that 2 is going to go to the right, but that is going to be splayed to the top. So every insertion and find gets moved up. Then what's happening is we're going to insert 3. It's going to be put in here, but then it's going to be splayed to the top. Insert 4. Insert 5. I'll put in 7 elements. And if we look at this by itself, it looks like it has the same problem that I mentioned earlier in the semester about binary search trees in the first place. It's the whole reason why we were doing AVL trees and B trees and web lab trees. We encountered this scenario in which the tree became a glorified linked list. But here's the thing, if I do find, if I put in 4, well, first let me put it plus pause. What's going to happen is, in a binary search tree, we would get to 4, and then we just stop. We're like, oh, it's in the tree, and then we leave it alone. But now we're going to do the mechanisms. What's going to happen is, we're going to see that 5 is going to become the right child of 4. And what that animation did is it did a zig-zig, right? So that was a double case, so it went zig, zig. So now 4 is going to be moved up, and 5 is going to be the right child of 4, and 6 is going to become the right child of 5. Everybody see that? And then what we're going to see is now it's going to zig. So now 7 is going to become the right child, and 6 is going to become the left child of 7. So now what happened is 4 is now close to the top. And if I want to access 4 again, well, it's just there. So if I want to, let's say I want to find 3, it's now going to zig up. But we're going to see this idea of locality again, and we're going to say 4. And now it's there. If I want to do 5, we see that 5 is a little lower. So 5, when I do find, we're going to splay it up and it's going to become the top of the tree, but you're going to see that what's going to happen is that 7 is going to become its right child. And then we get here, now I say, let's say I want to do 3 again. And then I want to do 4. We now see that if I consider 3, 4, and 5 to be close in memory, that after performing several accesses, they've now trickled up to the top of the tree. And so here's a mathematical justification where if we were doing binary search tree with an Amoritized case, we did the same thing with 8 accesses, we'd have 4.5. But then what would happen is if we were dividing it by 2, we would just say, instead of 1 plus, it would be 1 plus 2 plus 3 plus 4 divided by 2, because that would be the average. So we're actually getting a significant benefit from the binary search tree. And then accessing 1 brings it up here from the Splay tree. And now what I have in the slides is basically what I've demonstrated here. So afterwards, we get an average. We've reduced that average down from 4.5 down to 2.85. So over time, taking advantage of the splaying property reduces the average cost of find. And so when I do this in reverse, if I were to do 7 to 1 in reverse, I would have 1, 2, 3, 4, 5, 6, and 7 in a binary search tree. But now we're down to 1.85. So we're seeing that our Amoritized operations become better. And so what I would like to show you next, actually I have this already open. In this Splay Tree demo, this is a Splay Tree demo that is available at Carnegie Mellon. And this demo was actually developed by Danny Slater. Danny Slater is the inventor of the Splay Tree. And so I was talking to him about Splay Trees, and he said the thing about cache memory is you can demonstrate it much better if you just generate a bunch of nodes and then propagate a few up to the top. So what I'm going to do is I'm going to say, show me a Splay Tree with 100 nodes. And then initially what's going to happen is we see that, if I scroll all the way down, it's just a glorified linked list initially, right? So even when we have one of these. So what I'm going to say is I'm going to call my cache from 60 to 68, right? From 60 to 68. So I'm going to say I want to initially access 63. So once I click 63, we now see that 63 is now at the top of the Splay tree. And we see that 64, 65, 66, 67, and 68 are here. But if we scroll down, that 61 and 62 are still at the bottom. Now, if I click 62, where we're now going to see is that 62 is up here. Let's say I do 65. And now I'm going to do 61. And then 60. Now I'm going to do 67, 65, 66, 63, 65, 64, 62, 68. Does everybody see this? What's going on here is that after a few operations that are of high cost, that I have to bring the Splay element to the top, what ends up happening is afterwards, it's like I only have 9 elements in the tree. So I'm getting a significant benefit, and I don't need to go in this scenario where I'm cutting down and looking at all through all of these, right? So now if I use this and I want to move on to the next program, and I want to do 30 through 38, what I would say is, well, all right, let me do 32. So we see that 32 is down here all the way at the bottom. So this is our Amoritized worst case scenario. And I click 32 and we're going to see that 31's up here, but mostly the elements that are still up here are still in the 60s, right? But then if I do 34, it's now up here. Now we see that 34, 32, 31, we still have stuff in the 60s. I'm now going to say 30. Now I'm going to look for 38. $37, $33, $35, $30, $31, $37, $35. And now we see that after a few costly operations, if we're doing hundreds of these operations with this small amount of memory, we now have the benefit of the elements that we want to be closer to the top of the tree up there. Does everybody see kind of the benefit of the Splay tree? So this is really good for keeping track of memory. And that's why it was initially invented in the first place. So here in the slides, I show some examples of how they're all up here at the top. And then for Splay Tree, I've come up with some calculations here for average cost for those accesses if you have 88 elements, and I'm sorry, if you have 55 elements. I'll get it right out the third time. I have 100 elements of which I am trying to get to the 50 through 59. So the average is 55 for BST. I got to find that 55 elements if I insert it that way. And so here I have log of 100 of n log 100 plus 1 inside the red-black tree. So for a non-uniform seeking, if I'm focusing on certain elements, then the Splay tree actually beats the red-black tree. This is similarly to why in a hash table, we distribute using prime numbers. The reason why we did that is we have to account for the scenario in which the user does not do what we want them to do and is accessing in a non-uniform way. All right, so does anybody have any questions before I start digging into code? All right, so when I'm building the Splay tree, in the singly linked list node, I'm sorry, where's my, I apologize. I'm speaking the, singly linked list. I was teaching the fundamental students singly linked lists. All right, so with a splay tree, what I've done is I've used inheritance and polymorphism to build upon from the binary search tree. And what I'm using here is the different balancing mechanisms. But we have the same things inside the binary search tree node, right? So what's happening here is I have my splay tree that I have inherited from binary search tree. I have the same root node pointer. The binary search tree node is the exact same. And if we see private and public, what I've done is I've used for inheritance and polymorphism the constructor there for the binary search tree and the destructor by rule. And then I have the insert for the splay tree. And then I also have a method for contain. So I'm going to go over insert first. And an insert in the public method, what I've done is I've called in the private method root. And then once I find the location, I'm going to call a splay method. So insert, what it's going to do is we do what we normally did with the binary search tree. I say if the curve pointer is equal to null, I create a node at that location, and I save it equal to this BST node that I've called by reference. So I'm pointing at that location. Then if the value is less than, I would account for traversing the tree left or right. So it's pretty much the exact same thing. But then we're going to call the splay method to allow us to be able to splay the element to the top of the tree. And I've separated them out so that way I can call the same method in contains. In the splay tree method, that was the exact opposite of what I asked you to do. There you go. In splay, I'm passing a value and I have a parent and a grandparent. And this allows me to say that I'm a current node, but I can also keep track of the parent and the grandparent, so that way I can perform zig-zag and zigzag operations. So forgive me, I'm going to zoom out a little bit so this is a little clearer. Just like before, in any other tree operation, the very first thing I do is I check to see if it's not null to ensure that we don't have any memory or segmentation faults. In these first two if cases, I'm seeking the location of the element. So I say, here's the parent. If the value is less than the parent data and the value does not equal parent left data, then I'm going to call splay. And so that's, I'm also checking its grandchild, excuse me. And here I do the same thing with the right. So now once I get to here, what this means is that the element is in the tree, or I've found the location where we think it should be. So in splay, I'm just going left and right, and I just find this specific location. So here to recurse back up, we need to account for these four cases. And in each of these cases, I have a parent and a grandparent. And what I've done here is I've created temporary pointers so I can keep track of everything while I'm performing the operations. The next thing I do is I'm considering if the parent left is equal to null and the value is less than data, or the parent's right is equal to null and the value is greater to the data, then what I'm going to do is I'm going to say that I'm going to make that temp parent's data equal to that value. So all I'm doing is just moving up to the parent, pretty straightforward. The next thing I'm going to do is I'm going to create a temporary child pointer. So if we get past this, this means we got to start doing zigzag operations or zig-zag operations. And then what I have here is I have a temporary child pointer. And then I'm saying, well, if the data is greater than the value, I set the temporary child equal to the parent's left child. Otherwise, I'm going to set it equal to the parent's right child. Then I perform one of 4 cases. I got zig-zig left, zigzag left, zig-zig right, or zigzag right. So zig-zig left is in the case where the data is greater than the parent's data and the temp parent's data is greater than the value. So the value in this case should be higher. I'm sorry, it should be less than. So it's going to be left and left, zig-zig. Left and then left, zig-zig. So now what I've done, and I have animations to describe what's going on here, but here's the general idea. The temporary parent's left child is going to become temp child's right. So I have temp parent, temp child. Temp parent's left is going to go here to what temp child's right was. Then temp grand, this left is going to go to temp parent's right, like so. And then the temporary parent's right child is going to become temp grand. And then the temp child's right is going to become temp parent. And then we're going to say grand is equal to temp child, so it's going to move off of that. So let me find where I have the animation in the slides to clarify my explanation. Okay, so recurse, showing you all this. Huh, where's the slide? Ah, no fun. Okay, so I'll just draw it out. Okay, so what's going to happen is in the zig-zag scenario, I call it temp grand, I have temp parent and temp child. Does everybody see that? So what's going to happen is in this line of code, the temp parent's left, so if I call this temp child's right at X, temp parent was initially pointing here, but I'm going to update it so it's now pointing there. So that can be null, it can be a value, whatever we want it to be. Then what's going to happen is we're going to say temp grand left is going to be equal to temp parent's right. So we have the same thing here where that's equal to X. And temp grand is now left is now going to point there. Now what's going to happen is temp parent's right, which is originally pointing, I'm sorry, I'll just call this Y so it's clear. So what's originally pointing at Y is now going to point at temp grand, like so. And then temp child right is going to point to parent. So before it was pointing to X, it's now going to point to temp parent. Now the grand pointer was pointing at temp grand. That's what was called into the method. And now what we're going to say is grand is going to be updated to point to temp child. So then what's finally going to show up here is we're going to have grand, which is pointing to temp child. Temp child's right is pointing to temp pointer. Temp pointer is left is pointing to old X. Temp pointer's right is pointing to temp grandparent. Temp grand is now pointing to Y. Does everybody see how that zigzag worked? So the zigzag is just, we perform the same kind of tasks, except we check in these opposite scenarios. So temp grand data is greater than the parent and temp parent is less than the value. So instead of it being greater, it's greater and less than. But then we see that we perform the same kind of operations. We then do the same thing for zig-zag right, and then we do the same thing for zigzag right. And then I have a first level for Splay, and if it's if else, and forgive me, there's a minute left in lecture. So if the current data value, value is less than current data and current left is equal to null, what that means we've requested an element of the Splay trees that's smaller than the root. So therefore we just return. So now we just say that that element is there. And then we have that same scenario if the element that we've requested is greater than the root, and it's just, and that's the root's right element is null. So therefore that element we need to display as root. Otherwise here, what we're performing is just a zig operation where we're making, in this case, it's we're rotating left. So temp parent's left is going to be temp child's right, and temp child's right is going to be the temp parent. It's going to rotate like so. And then we just do it the opposite way for zig right. Otherwise, if the value is less than, then we call our zigzag check method. And then we would call it the opposite way for the left. Okay, so does anybody have any questions on this? All right, so the thing that I will evaluate on an exam is your ability to insert, splay, and then find. So the problems that you'll see on tonight's review assignment, that's what will be what I will evaluate on the test. All right, so if anybody doesn't have any questions about what's going to be about Splay Trees or what my expectations are for the pre-internship for tonight, then you're all dismissed. Yeah. Okay, I will bug him. Thank you for bringing that to my attention.